Hello, I'm Mr. McBrien. This is Turing 5, Working with Numbers. Yesterday we talked about the screen. We talked about displays, we talked about screen resolution, we talked about colors and fonts. Today we're going to actually view things from under the hood instead. Instead of talking about displays and things like that, we're going to talk about numbers. So we're going to talk about random number generation, a little bit about simulations, talk a bit about remainders, and a few applications of some of these ideas. Okay, so if we want to think in terms of numbers and software, we can think about answering simple questions. For example, what's 4 plus 4? We've already done. Or we can talk about answering some more challenging problems. And these are some of the biggest applications of software today. So some of these problems. How much money should we charge people for insurance such that we make enough money? Or we can argue, how much should we charge for insurance such that we maximize the amount of money we make? We can ask ourselves what stocks or bonds we should invest in our hedge fund this year. We can ask ourselves if the Earth is getting warmer, or maybe a tougher problem. We can ask ourselves if we can prove that human activity is what is making the Earth warmer. We can ask ourselves a frightening problem. What will happen if the Earth gets 3 degrees warmer? We can ask ourselves some huge problems, huge questions. Is the universe expanding? Does dark matter really exist? These are the kinds of things that mathematical models can help us with varying degrees, of course, of certainty. So, this is a whole very large discipline, is statisticians using computers to answer questions along these lines. Questions that are hard to answer purely from observation. So, by the way, this is an area of expertise for me. I spent over a decade designing systems for solving these kinds of problems. We're not going to go into in-depth aspects of this. In fact, there are degrees and postgraduate degrees associated with those things. We're going to talk about some of the simplest tools for starting us along that path. But really, since there have been computers, there have been scientists trying to model natural processes using computer simulations. What we will talk about today will be just an introduction to some of the simplest of these tools. And the first one is something rather fun. Random numbers are something that has been fascinating for a very, very long time. The idea of a number where we have no way to predict what number will be produced. There are physical models for these kinds of things, but we can use them inside software as well. We can use them to make programs unpredictable. So we can use them, for example, in games. We can use them to simulate opponents. We can use them to create opponents that are imperfect, having them make mistakes once in a while. We can have them make opponents unpredictable, where the opponents will do something different the next time that you face them. We can also use them to test hypothetical situations. So we can use them to approach given problems. And we're going to examine one in some detail today to illustrate an idea in the real world, when these concepts are used, it's more complicated and would require more discussion. But we don't want to do that here because we want to just discuss primarily the tool. But if we want to use these random numbers, we have to have an understanding of probability. Some of you may have better grasps of this than others. We will use one of the classic random number generation tools from history in order to illustrate some of these points. So first, let's talk about how we generate a random number. We do that with a simple command. We can, first off, declare our variable, and then we can generate a random number. In this case, as you can see from my comment line, we're generating a random number between 1 and 10. But I alluded to the idea of talking about a random number from history. There's documentation of gambling based on dice well over 2,000 years ago. How would we simulate a die rolling? Well, really all we do is generate a random number between 1 and 6. And so I've written the code here. And this is the code for a very simple application to roll a die on the screen. If we trigger the application, it'll give us a random number between 1 and 6, or roll a die. So, yeah, that's a fairly trivial kind of thing to approach. We can go ahead and model more complicated systems if we want to, or we can start to ask ourselves some fundamental questions and then test them. Remember, probability is all about measuring. It's all about what would happen if you did it a whole lot of times. At any rate, we can look at real-world probabilities, consider our situation carefully, and do things like modeling rolling 2 dice. And before we start, let's consider some boundary conditions. If you roll 2 dice, what's the minimum number you can get? Think about that for a second. You realize it's a 1 on each die, and so the minimum total you can get is 2. 1 plus 1. And if you ask yourself, what's the maximum you can get? Well, that's pretty trivial as well. It's 6 plus 6, or 12. Now here's where things get interesting. We can be tempted to reject context and say, okay, we can simulate 2 dice rolling by just giving a random number between 2 and 12. And if we do this, our simulator, we may not be able to tell from a single roll. We may not be able to tell from 5 or 6 rolls, but our simulation would be wrong. So I'd invite you to pause the movie for a second and think about why this would be. Okay, welcome back if you paused it. Did you figure out why a random number between 2 and 12 would be wrong? Well, actually, I'm going to let you go ahead and write code to further probe this, to try to work it out yourself. So, if we want to write an application to roll a user-defined number of dice, output the rolls obtained and the sum of the rolls, this will illustrate the problem with just doing a random number between 2 and 12. So if you go ahead and implement this, so you can allow the user to define, for example, 4 dice. You can put a maximum on it if you want to, and output the rolls that were obtained. you'll see that a random number between 2 and 12 gives a very different result for 2 dice than the sum of the rolls. Why? Because there are fewer instances where you can get a total of 2 or a total of 12, and many more instances when you get a total of, for example, 7. And so as long as you use the approach of writing an application to output each roll individually and then total them, you will have implemented a good model. A bad model would have been this random number between 2 and 12, because it would have given the same probability of a 2 versus getting a total of a 7, for example. Hopefully that's clear, but if you implement this code here, it should be obvious very quickly, the error in that. So, but here's a very fun thing, and this gets closer to the kind of thing that I was talking at the beginning of the movie. It's all fine to allow a user to specify that we're going to roll 6 dice, for example. But if we want to try to get an idea of what average value you get, for example, if I said you can have $1 for every, they're called pips, for every pip that comes up when you roll a die, you can have $1 for that. How much would that be worth to you? If I said, for example, if you pay me $3, you can have $1 for each pip on the die, would you take that deal? This gets very close to this hedge fund problem. If I said you have to pay me $4 in order to roll a die, would you take that deal? Well, this problem on the page right now, if you rolled a die a very large number of times, what value could you expect to get for the average? I'd invite you to think about that for a minute. And then here's the fun part. After you've thought about it, put your answer down for what you think the average should be. Now, write the code to roll a die 1,000 times, for example. Or if you're not confident about that result, roll it 10,000 times. These are the kinds of things that software can do. It wouldn't be feasible for us to roll a die 1,000 times and make observations and write them down. But software can do this. And this is a phenomenally powerful tool. So if you were tempted not to implement this piece, not to do this activity, I'd invite you to reconsider and give it a try and have a look at the result. Because it's just a loop. It's not that hard to implement. But the value in terms of understanding what's going on is really quite high. So go ahead and implement that and think about the implications and think about the ways you might possibly use this kind of thing. And we'll come back in a minute.